This video is an example problem showing you the motion of a charged particle in an electric field and in a gravitational field, one field on top of the other. To begin with, you can see the basic setup. I've got two plates connected to a battery, and the particles can be shot between the plates at 4,000 meters per second, and the plates are 5 millimeters apart, and it's an electron because it says E minus. Now I've even given a couple possible paths. It says what path would the electron follow, what are the x and y coordinates of the electron after 10 nanoseconds, assuming it starts at 0, 0. Remember that a nanosecond is 10 to the minus 9 seconds. We'll need that later. So if I look at my givens, I've got the distance between the plates at 5 millimeters, the voltage at 1,000 meters, the charge of an electron 1.6 times 10 to the negative 19 coulombs. Notice I didn't use the negative sign on the charge because I can figure that out from the problem. And I have the mass of an electron, which I know because I can look it up. Alright, first thing I need to do is figure out what the signs of the plates are. So I look at the battery, the long side's positive, the short side's negative. That means that the top plate's connected to the positive side, so it's positive. Bottom plate to the negative side, so it's negative. Cool. Now to figure out which way it's going to curve, I've got to figure out the direction of the net acceleration. If the net acceleration is upward, it's going to curve upwards, that's positive. If the net acceleration is going to be 0, it's going to go straight, that's a horizontal. And if the net acceleration is negative or downwards, then I know it's going to curve downwards. To find the net acceleration, I'll use a free body diagram. So on my charged particle, I have two forces. The first force is due to the gravitational field, and that's W equals mg, that force. And the second force is due to the electric field. So I've got two forces over top of each other. Fe is my electric field's force. So now what I'm going to do is find the magnitude of the gravitational field, W equals mg, and I get the weight of the force due to the gravitational field to be 8.927 times 10 to the negative 32 newtons. Now to find the electric field, I'm going to use F equals QE, but before I can use E, since it's not given, I got to find it. So I'm going to use V equals ED to define E as V over D. Then I'll use my F equals QE formula and replace E with V over D. Putting in my numbers, I get 3.2 times 10 to the negative 17, which is a whole lot bigger than the weight of the electron. So when I find the difference in these two, the forces going up minus the forces going down, that's going to give me 3.2 times 10 to the negative 17 newtons. Not a difference, really big difference in force. It's the same thing as the electric force because the weight is so small. If the forces were pointing in the same direction instead of subtracting them, I would add them. So in this case, this tells me my net force is positive, so it's going upwards. Since it's going upwards, that tells me that the curve that I need is going to go upwards. So a negative net force would have been a downward curve, a net force of 0 would have been horizontal, but this is positive, so it's going to curve the particle upwards. So that's problem number 1. Question number 2. So for question number 2, I got to find the coordinates after 10 nanoseconds. It's kind of like a projectile motion problem. I have two givens, one horizontal and one vertical, two accelerations. So vertically, it's not going up or down, that's 0. The time is 10 nanoseconds. And if it were a projectile motion problem, I would write negative 9.8 meters per second squared at the bottom. Horizontally, it's traveling at 4,000 meters per second. Horizontally, or whatever direction, it's 10 nanoseconds. And horizontally, the final velocity is 4,000 meters per second. Now remember, the net acceleration is going upwards, so that means it's not going to act like gravity. I've got the net of two fields acting on it, gravity and the electric field. And I found the net force to be 3.2 times 10 to the negative 17 going upwards. So now what I've got to do is find the acceleration. And I know that vertically, it's not going to be negative 9.8. So I'm going to use F equals ma to find the net acceleration. So a is equal to force over mass. So the acceleration is 3.2 times 10 to the negative 17 times, or divided by the mass of the electron, to give me 3.51 times 10 to the 13 meters per second squared. That's what I'm going to use for my acceleration, the 3.5126 times 10 to the 13 meters per second squared. Great. So now I've got to find its y position and x position. So I have the initial velocity, the time, the acceleration, and I'm looking for x, or y if you want to use those variables. So I'm going to use y equals y naught plus v naught t plus 1 f a t squared, using the 3.51 as the acceleration and putting it in there, and the time 10 times 10 to the negative 9 squared. So that gives me a y position of 0.00176 meters. The x position, there is no acceleration, so that's great. That's just 4,000 times the time. That gives me 0.000040 meters. So the x and y coordinates are 0.000040 meters, and the y is 0.0018 meters. Here's a quick summary of what all is happening. I started off by finding out the signs of the battery to figure out the signs on the plates. Whatever's connected to the positive is positive plate, whatever's connected to the negative side of the battery is the negative plate. To do the first question, follow the path. I knew there were three choices. And what I did was I found a free body diagram to determine the FNet's direction. In this case, it went up, so it curved upwards as one of the choices. For problem number 2, I treated it like a projectile motion problem where the acceleration in the y direction is not negative 9.80 meters per second squared. And then I find the acceleration using a free body diagram, and F equals ma to find the acceleration. The free body diagram helps me with the direction of the force. Then I'll use the vertical givens and kinematics to find the x and y positions. And that's what I did to solve this problem. It's not a quick problem to solve. It will take a lot of work to get through to get the final answer.